Welcome everyone to another episode of our book club author chat. This month, our book club is reading the book Causal Inference in Python, and we're super grateful and honored to have the author of the book, Matheus, join us today. Welcome, Matheus.
Thanks for the invite, Sophia. Do you want me to go over the slides you had me prepare, like
Yes,
introduce the book or something? Okay,
that would be awesome if you could introduce yourself and the book. That would be super helpful for us.
like probably take 5 minutes. It's just like a brief overview of what the book's about and a little bit about me. So I graduated in economics. I'm on the rare cases where I work in my field of graduation, let's say. I work in banking with economics, and I've been working with economics and banking for a long time now in Nubank. I've worked mostly in credit models, although I ping to sometimes I work in marketing too, which are very fields that have a lot of causal inference and economics attached to them. I also worked sometimes in collections, where essentially is the bad part of banking, where people don't pay their bill. We have to figure out a way to make them pay. At some point during my career, I became a manager. I didn't like it. I lost all my humanity and life essence. I moved out of collection back into credit again. I became a manager because I was too stressed out. And I started working with causal inference model. So even though I've been working with causal inference in research for a long time, I got to apply it only recently in my career, only late in my career, let's say. Now I'm sort of like a causal inference specialist in my company, which means I work kind of like an internal consultant. So there are multiple problems that touch causal inference. They call me, I go there and do some consulting stuff. I also have my own projects, which are mostly related to credit. While I was doing this, I wrote some books, this one in particular, and another one which is open source, which is Causal Inference for the Brave and True. I had a kid. I took a long time off. Now I'm back to work, and I'm working with credit again. Like I really enjoy credit, and I think it's a fascinating business. So about the book, it is structured in parts. So part one is there's nothing innovative in the sense of part one. It's like fundamentals. So the first part introduces the notion of a counterfactual, which essentially is like, okay, what would have happened if I did this instead of that? So the first chapter basically explored this idea in length, just to introduce the reader to counterfactual and the notion of bias, like what's the big deal with causal inference, why it's so hard, and how can we think about it. Chapter 2 focus on randomized experiment, which is a very simple way to deal with bias, but it's mostly a chapter about stats review. Like causal inference, there is the causal part, but there is also the inference part, and I sometimes feel that folks forget the inference part, which is very important, and I don't want to I didn't want to leave it behind. So chapter 2 is mostly a stats review, and chapter 3 is essentially it's mostly theoretical. I think it's the hardest chapter to read because the book tries to be very applied, but there's this chapter is very theoretical. So it focuses mostly on graphical models and how to structure your causal inference thinking. Even though it's not very, let's say, there's no direct application of this, I feel it's the language of causal model is so powerful to make us think clearly about causality that I really wanted to include this in the book and in the beginning as chapters for fundamental. And this covers all the fundamental, and then we go to part 2, which is essentially dealing with bias, so adjusting for bias. So there are 2 main chapters here. The first one is linear regression, and I wanted to give it's linear regression, but not in the perspective of machine learning. It's more of in the perspective, it's like a hidden, the chapter is called linear regression, but it's really about orthogonalization, which is one of the 2 main ways to remove bias from your data. And the other main method to remove bias is propensity weighting. So here, which is chapter 5. So part 2 focus on those 2 approaches to deal with removing bias from your data. Then we move to part 3, which focus on effect heterogeneity. I'm of course biased, but I would argue that most of the industry applications are in this part, because when you're applying causal inference in the industry, most of the time you don't have to deal with bias. I know there are some cases, like particularly in marketing, but in most situations you control what is called the treatment assignment mechanism. So you can, like, bias is not much of an issue for you if you're in industry. It's more of an issue if you're in academia, because you have to untangle a bunch of associations from causation. But in industry, since you control the treatment, is a lot easier. A lot of times you can just randomize the treatment and bias is no longer an issue. But there is a very huge interest in the industry of effect heterogeneity and personalization, which essentially is like finding people or groups of people that respond different to a treatment. Like people that are more sensitive to prices, to discount, to an email versus another email. So it's essentially figuring out how to personalize whatever treatment your company is trying to optimize, like be it email, be it price, be it interest rates. So essentially trying to figure out if people respond differently to that treatment. And chapter 7 is just a bunch of models to tackle the problem presented in chapter 6. After that, we move on to panel data. Panel data is, even though in most applications in industry you don't have to deal with bias, there's a big chunk of the work in industry which is marketing, and where causal inference is very useful to solve to study marketing problems in the industry. And inside causal inference, I feel panel data is like what people go for when they want to understand the impact of marketing campaign. So I had to talk about it here. Chapter 8 talks about difference in difference. This was a very hard chapter to write because the difference in difference literature grew a lot in the past 2 years. So I had to include a bunch of flavors of difference in difference about a bunch of things that changed. So somehow a lengthy chapter. And synthetic control too. So another flavor. It's not too different from difference in difference, but it applies in situations where difference in difference might suffer, particularly when you don't have a clear model for the trends of the control groups. And finally, part 5 is about alternative experiments design, which is essentially like sometimes randomization is not an option. For instance, in marketing, you cannot randomize people that are not yet your customers. Like you can randomize who gets to see your ad campaign. So you can do stuff like geographic experiments, so randomizing regions or countries. And so essentially you zoom out your unit of analysis. Instead of you looking at a particular customer, you look at a group of customer, in this case, a geographical location, and you can randomize those. And also switchback experiment, which is essentially you have only one unit of analysis and you want to understand the treatment effect on that unit of analysis. So you take the treatment and you turn it on and off, on and off, on and off, and you see what happens to the outcome. And how do you analyze those sorts of data? Switchback experiments, they're usually applied in industry where you have some sort of marketplace, like if you have a delivery company where you have to match delivery folks with people ordering. So we have some sort of marketplace. And in this case, switchback experiments are very interesting. And chapter 11, it's mostly for the sake of completeness, talks about IV. And inside IV also about regression discontinuity designs. I feel like this chapter is useful in very specific situation in the industry. I confess I haven't found a lot of use case for IV in the industry, because we're usually not interested in if we have an instrument, we're not interested in the treatment effect, we're more interested in the intention to treat effect in the industry. But regression discontinuity design sometimes find its use more in industry where like we apply some sort of thresholding. This is kind of common in industry, like you want to define a prime segment of a customer. So you say, oh, customer that spend above X, we're going to treat them differently. So you essentially apply a thresholding decision in the way you treat customers, and you can leverage those sorts of thresholding to analyze causal inference even without experiments. So it's some neat ways you can also deal with causal inference, even though you might not have a way to randomize and to deal with bias. And that's it.
That's awesome. Thank you so much for the great introduction. I feel like this is a must-read book for data scientists. I wish I have read this book when I started my data science career. Yeah, so I have a lot of questions, but before I start asking my questions, I want to open the floor to the book club members here who may have questions. So if you have any questions, feel free to ask directly, either in the chat or just unmute yourself. Otherwise, I will start asking. Anyone? Okay, fine. I'll start asking my questions, and if anyone has any questions, feel free to ask whenever. I will start with general questions first. This one actually is from our book club members on Discord. How do you approach problems in real life? Because in the book, it kind of presented a incremental approach where you start with something simple and then try more complex stuff as you go. So also it seems like in the book, there's a lot of simulated data where you know what the result is, but what about real life that you don't know what the actual situation is? How do you know if a technique you're using is correct?
Sorry, I lost them. Yeah, here. Good question. I would say it depends on the problem. So let's pretend we have a problem where we can randomize, because those are easier to deal with. So if we can randomize the treatment we're interested, just for the sake of completeness, let's say you're a company and you want to optimize discounts that you give on your product, right? So you want to find how much discount coupon you give to each types of customer. I think one of the biggest challenge in causal inference is that, unlike machine learning, you don't have a ground truth. So it's not like you can throw it a bunch of models, like you can't do the meat grinder approach where you just throw a bunch of stuff and see whatever outputs the highest metric, because you don't have a ground truth. Like in chapter, I forgot the chapter, but in this chapter, in the effect heterogeneity chapter, I try to give some metrics for counterfactual. For instance, you have you can do a target transformation where you have a target which in expectations approach the thing that you care about, the treatment effect. But it's only an expectation and it's very noisy and it depends on nuisance model. So you have to estimate a model just to get your ground truth. So it's a very challenging part because you don't have ground truth. So yeah, that's a tough problem. So how do you approach this in real life? Usually what I do is I gather random data, and the better the experiment, the simpler the experiment, the better. And I'll use this random data in a way to generate counterfactuals. So if you have a large enough experimentation data, you can simply average over the treatment and gather the outcome to see what are the counterfactual outcome. If you care about specific, like what's the average what's the counterfactual outcome for this specific groups of customer, it becomes harder and harder because the dimensionality of the problem grows. But still, if you have random data, is already a very great start, and you can apply the metrics that I presented here in chapter 6, which are essentially like there are some metrics where you can use metrics of divergence, like mean squared error with respect to that transform target I mentioned earlier. So there are some causal metrics. I admit that this is an active area of research, but if you have experimental data, it's much easier to trust those causal inference metrics. So we have metrics, and essentially we can turn the problem, like not exactly, but into sort of like a machine learning problem where you're maximizing mean squared error or R2. Like just throw a bunch of models and see whatever performs better on your randomized data. So I don't even care about if I have randomized data to fit my models. As long as I have randomized data to validate my model, then I sort of transform the causal inference problem into a cross-validation and machine learning model where I just try a bunch of stuff and see whatever performs better on the randomized data. So this is usually how I tackle. Like I see if I can randomize it, I design the simplest experiment as possible, where it's easier as possible to use that experiment to generate trustworthy metrics, evaluation metrics for whatever model I'm trying to use.
Thank you. I think that's really insightful. I think one of the key point I learned from the book and also from our conversation just now is that you can do cross-validation with causal inference, which I have never done that before. So that's really good to know. Yeah, I only use that in the machine learning context, but in causal inference, you can do that as well. We have several questions from the chat. Would you like to take a look and see which one you would like to answer?
Yeah, I'll answer them in order. So Carlos, I guess he's from Brazil, from the name. Welcome, Carlos. What do you feel is the book's greatest contribution? Okay, also great question, especially for me because it's really easy to plug in my book here. I guess when I looked at, well, I read a bunch of causal inference books, and I mean a bunch of them, even before like causal inference was a hot topic. There was already causal inference books, but most of them were focused on academics, and there were two kinds of books. Books on econometrics, like if you have Mostly Harmless, which I really love the book. You have Causal Inference Mixtape from Scott, which I also really like. You have The Effect, which I also really like, but they're mostly focused on academia. And you have some books that are about biostatistics and epidemiology. For instance, Hernan's book, which I think is called What If Book of Causal Inference, and mostly targeted to the health field, like epidemiology. So there wasn't, well, at least not that I know of, a book that was targeted towards the industry. Like, how do you apply causal inference in the industry? What are the main challenges? And like I mentioned earlier when I was introducing, like the problems, some are the same, but some are very different. Like industry is mostly worried with effect heterogeneity, which is not a big concern for academics. So although the techniques are the same everywhere, the focus on the industry is much different, and I couldn't find an easy book, like a welcoming book, a book that was easier to read and for people that just wanted to apply this in their work to use. So I wrote this book. I also wrote another book, but that other book is kind of also focused towards academics because it's kind of it's essentially a translation of Mostly Harmless econometrics to Python. So that book did not cover what I wanted to talk about in causal inference in Python. I guess the approach to industry is something that I felt the gap in the literature that I wanted to cover. So next question, what kinds of attributes you want to see in one data scientist needs to focus? Okay, what data science needs to focus more? I think it depends a lot, but well, don't take this at face value, because one thing that I really wanted data science to focus more on is really understanding the problem that they're working with. I see a lot of time data science just throwing a bunch of stuff in the machine learning model and treating us like a meat grinder. Just optimize the AUC out of this model, and we're good to go. Which I think has like this is important. Like I'm not saying it's not. I think really understanding the models, the fine tunings of the models, and how to make the models better is a very important thing. But I missed the part where data science really focus on, okay, what exactly is the distribution of data that we're working on, and why are we building this model? Usually it's a predictive model, but why are we making this prediction? How can we use this prediction in reality? And what can make these predictions go astray? So what I found is that, like, if you build a machine learning model, most of the time you're not just interested in predictions, you're interested in counterfactual prediction, which is you want to understand what will happen to some y variable if you change a treatment, which is essentially a causal inference model. So you build a model, you figure out what it predicts, and then you make a decision based on those predictions. So you're essentially using your model to make decisions. And oftentimes, those decisions change the way change the data of your model. So by using your model, you're essentially causing a distribution shift, which completely messes your model. So there is often this behavior you see in the industry where you train your model, you did a very good job of cross-validating it. There's no leakage, it's perfect. Like the metrics performance of the model is stable across time, and then you deploy the model, and then the predictions drop dramatically. But how does that happen? Like you validated, you cross-validated, there's no leakage, your data is very good, but even so, the prediction of the model decayed once you deploy the model in production. And the reason for that is when you deploy the model in production, it shifts the data. Like it makes decisions that make people act differently. And the model never saw that data because it did not took into account the way that the actions of the model will output influence back on the data. But essentially, you did not look into the problem as a causal inference problem where you want to understand how the actions that you're going to make affect the behavior and affect the data that you're going to feed into your model. So not knowing that, not understanding how your model is going to be used and how the decision that your model outputs impacts the data, I wish the data science knew more about that. So next question. I have a hard time explaining to management the difference between ATE and okay. So I have okay, I understand. So I guess the question is, what's the difference between the treatment effect and a difference in average? So simply comparing the average of the treatment with the average of the control will not, in general, recover the treatment effect because of, well, all sorts of bias. And any advice on that? So one advice on that is that I think it's more of a cautionary tale. When I joined the team of data science in Nubank, I was the only economist there, and most people working from computer science. And people from computer science, they have a very different way of seeing the problem. So we had a causal inference problem, which the team was approaching as a prediction problem. And because of this mismatch of classifying the problem as a prediction when it was a problem of counterfactual, the problem, we were not able to solve the problem. And I saw that, oh, you're mislabeling the problem. This is not a prediction problem. I told them that. It took me like two months to understand what the problem was and to propose a solution. But it took me 2 years to get them to really convince them that that was indeed the solution. So I feel the pain, like folks that work in causal inference, it's hard to make our voice heard because computer science folks, which dominate data science today, they're not used to understanding the language of causality. And I guess communication is a lot of the challenges in communication. So along those 2 years that I've tried, that I spent convincing and really understanding the problem, I guess what I learned is that the best way to teach people is like, I don't think you don't have to dumb it down, but you have to make it very clear. And I really like drawing very clear pictures. Like, this is what you have, and this is why what you have is not what you want. So try to understand, to explain this with lots of examples, lots of images, simulating data, which shows why the way we're tackling things don't work and an alternative way works. So tackling it from different angles, because causal inference is not intuitive, and trying to make intuitive is a tough job. I think that's the way to go. Like, try to make it visual, try to give a bunch of examples, try to understand, try to explain why it doesn't work, and be very clear and be very tangible with your examples. I think that's more of the way to go. Do you recommend as a prerequisite to your book this series? Let me click on the link. I really like the series by Ati and Weiger, I think. I based a lot of the book, part of the heterogeneous treatment effect part of the books on this series. I don't think this is a prerequisite. I think this is more of like, if you want to learn more, go watch this series. Like, this series covers in much more detail what I had to cover in like 2 chapters. So I guess if you really want to delve into treatment effect, heterogeneity, and personalization, I think this is a great series to watch. Some of the downsides which I don't like about the series is that it's in R, and I think R is it's a little complicated to use. And also there is the other downside, which is it focused mostly on causal forest. The algorithm is very great. Like, I really like causal forest, and I'm sad that I could not cover in the book. The reason why I don't like it, the reason why I did not cover causal forest in the book, and why I don't like causal forest, is that as of today, we don't have a decent algorithm in Python to run. Like, I've tried a bunch of times, it takes forever to run, because most of the libraries, they implement the tree in native Python. So while you want something ideally implemented in C++, something like that. So if you run an XGBoost or even scikit-learn tree, it runs super fast. But if you use any of the causal inference libraries that implement causal forest, they're so slow, it's like impossible to use. Which is why I feel that we still don't have a software solution to use causal forest in the industry. So that's the other reason why I'm not why not that one of the downsides of this series. But other than that, I think it's great. There is this section of the loss function, which ties back to Sophia's first question. Is like, can you define a metric, even though you cannot see the counterfactual, even though you cannot see the treatment effect, can you at least define a proxy where you can use to transform your causal inference problem into a machine learning problem? So I think this series covers this in great detail. So moving on, question from Danielle. When you cannot randomize your treatment, how do you approach problem in real life? On chapter 12, you approach the causal discovery. Do you see that it's being applied to industry in order to build DAG? Okay, so there are 2 reasons why, well, I think there are 2. Remember that my experience is very limited to one industry, which is banking. But some reasons I can think of where you cannot randomize a treatment is, first, the treatment is very expensive. So in banking, for instance, one of the treatment is how much money you give to people, like a loan. You want to understand how much money you want, how big is the loan. You cannot simply randomize loan amounts to people, because this will be extremely costly. Like, you cannot simply give $1,000 to someone that is very risky. This would be an extremely expensive experiment. So you cannot completely randomize. And the other situations where you cannot randomize your treatment is because you simply cannot allocate it to the folks of interest. So I think marketing is the best example for that. You cannot randomize who sees your advertisements. So this is a challenge. There also, I just remember a third way where you can, when you cannot randomize the treatment, it's more of a situation where the outcome variable is very long term. So even though you can randomize, if you randomize today, you only know what happened in like 2 years' time. So ideally, you want to use the data that you already have in the past to do some sort of causal analysis instead of having to design an experiment now and wait 2 years to see the results. So there is this third category where it's not that you cannot randomize, but you would rather not have to randomize. So the way to tackle all of those approaches differ. I think if you're working with something like marketing where you really cannot randomize your unit of analysis, one thing to try is to change the unit of analysis. So instead of looking into customers, which is what you would randomize if you could, you look, for instance, for geographical locations. So even though you cannot randomize who gets to see your advertisement, you can deploy your advertisement in different cities or different states, and that you can randomize. Like you can randomize the states, you can randomize the cities, and essentially you zoom out, you change the unit of analysis into something you can randomize, or you do some sort of switchback experiment, which essentially you cannot randomize who gets to see your treatment. Maybe you can only deploy the treatment either to everyone or to no one. So what you do is that you keep turning the treatment on and off and see what happens. So this is called a switchback experiment. For the case where the experiment is very expensive, you can design what I call, I don't know what's the technical name for this, which is called a conditional random experiment. So for instance, let's say you're trying to randomize a very expensive medicine. So you don't want to simply give it to everyone. You want to prioritize giving to people that are likely to benefit from that medicine. So what you do is that for people that you think are likely to benefit, you randomize it with a higher probability. And for people that you think are less likely to benefit from the medicine, you randomize it with a low probability. So essentially, you have two random tests. You have bias because you gave more of the treatment to people, to a segment of the population. So you've biased your treatment. The treatment is not independent from your covert. But because you know how you did with the randomization, using some sort of techniques from part 2, like inverse propensity weighting, to remove the bias that you introduced, you can do that to greatly reduce the cost of your experiment. So you introduce a little bit of bias, you reduce the cost of the experiment a lot, but the bias that you introduce can easily be removed with something like a regression or inverse propensity weighting. So this is the, like, again, depending on the situation that you cannot randomize, you tackle it differently. Feel free, like, if you want to give an example for me to give it a shot and be more specific on what you're thinking, feel free to shoot up a follow-up comment. So next one, do you have any suggestion if one wants to learn causal inference by working on side projects? Are there any good suggestions? Yeah, that's a tough one because, yeah, I get this question a lot because unlike machine learning, what you're really interested in causal inference is that you want to be able to deploy your treatment and see what happens, like, which you cannot do with static data sets. Like if you have a data set, there's no way to allocate the treatment and see what will happen. My recommendation is to work with reinforcement learning and to try to apply causal inference in the setting of reinforcement learning, because reinforcement learning gives you an environment where you have, like, the problems are very similar. In reinforcement learning, you have an action and you want to find a decision rule which allocates that action in a way to optimize some sort of outcome, which is essentially the same problem of causal inference. Like, but we call them differently. Like the action, we call them treatment, and that's that. Like we want to find the treatment, a rule to allocate the treatment in such a way to maximize an outcome. So if you have some sort of reinforcement learning environment which simulates a business environment, I would go for that. I don't have a specific recommendation for it now. I'm actually working on something like that right now, which I'll release it, which essentially simulates a lending situation for people to be able to test out their causal inference approach. Because again, I get this question a lot, like, how can I test this if I cannot really decide the treatment and see what happens? And yeah, there's not much you can do on side projects. You can either simulate the data yourself and see how the treatment allocates, or use someone else's simulation, which essentially look for reinforcement learning environments which can simulate those treatment allocations and outcome loops that you can translate to a causal inference setting. Alex asked if I explored encouragement design in my book. No, I did not look into that. It's a blog, I think, from Spotify. I'll definitely check a look, because again, like I mentioned, I don't know if Alex was here at the beginning, but as I mentioned, for me, I still have challenging to finding a proper use case for IV in the industry. So I'm very interested in looking to what they done here. Oh, I guess Sophia said that I actually covered encouragement design, which I guess is essentially like IV. I don't know if, oh, it's just the same thing. Sorry, I'm reading as I go here. So if encouragement design essentially means IV, then yes, it's covered. So Jing, I'll read question 1 from Jing. So first, so question 1, as a data analyst in the field, I'm always concerned about the reliability of causal inference and experimental result. This includes the aspect of result reproducibility. To facilitate trustworthy decision-making, I'm curious about the procedure you follow for evaluation when experimental results are obtained. I guess it's in a similar vein from Sophia's first question. So first, a disclaimer. I don't think we have a good answer for this question. We have ways to design metrics that are at best proxy metrics for what you care about. So in the book, I cover a lot about gain curves and cumulative gain curves, which is essentially a general, I don't know if someone already studied this, but gain curves and cumulative gain curves is a generalization of something that is called Gini curve, but is a way to understand if you have a good way of sorting your customers into most sensitive to the treatment to less sensitive to the treatment. So if you're trying to come up with a way to segment your customers into customers that are more sensitive to the treatment and customers that are less sensitive to the treatment, the Gini curves and the gain curves work up as a proxy for that. They require you to have unbiased data or experimental data in some sort of way. So if you have that, you can use, and if your goal is to segment your customers into those cases, into more sensitive and less sensitive, then you can use metrics like the gains and the gain curves. The other metrics, a lot tough, is when you want to understand counterfactual prediction. So you want to understand what will happen to this customer if I take this treatment, if I give this treatment to this customer? And this is very tough, because you cannot see what happened unless you give this to the customer. I offer one solution for this in the book, which is a target transformation approach, where you can take your y variable and transform it into something that is not the counterfactual you want, but it approach it in expectations. So again, those metrics, I understand they're not ideal, they're only proxies, and I think we as a field need to figure out better solutions to transform our problem into, like, how can we make a causal inference problem as close as possible to a machine learning problem, because then we just do cross-validation and it becomes a much easier thing to do. I think the trustworthy of your metric will depend on how good is your experimental design, because you really need unbiased data to run all these metrics. And also another thing that you can do to, I think this one really works actually, but it's not always doable, is, okay, you build your model, you validate it on experimental data, but now you're going to deploy your model in production. And if everything was right, what your model says will happen, will happen. So you validate on production data. I understand, again, not ideal, because ideally you want to validate, you want to do model selection before deploying your model to production. But after you deploy your model to production, you can at least see if things were according to plan. And if they didn't, maybe you can go back and reiterate and do stuff like that. So what I usually do is gather a very good experimental data source, do model selection using that data source, and then deploy the model in a very small sample of the customer and see how the metrics behave. If they misbehave, go back and reiterate. If they're great, if they work as expected, now we can certainly be sure that the model is working and it's reproducible in the sense that what it predict would happen is in fact happening. So follow-up question. I'm curious about how you utilize causal inference to enhance decision-making. When I work in the gaming industry, I'm interested in how you apply it in different fields. It seems that decision-making process in the gaming industry might be somewhat rigid. Okay. Again, I can only give the example of my very limited experience in banking. The three most interesting decision-making process that a bank does, well, the two big decisions that a bank has to do is how much to give people and how much to charge for that, which is essentially interest rates. So what we do is we use causal inference to build an automated decision system which allocates how much people can get and what are the interest rates which charge for whatever they get. So you essentially think about what you want to do is you want to build a machine that makes decision automatically. This is one way to tackle the problem, right? You can have the other way, which is have humans make the problem and machines only informing the humans. So instead of doing this, you can have people deciding how much to give to customers. So essentially, if you want to get a loan, you have to go to your bank, you have to go to a branch account, you have to speak to someone, you have to go with a lot of documents to prove your income. And then that person is going to say how much loan you can get. And maybe that person is also aided by some sort of model, but ultimately the person makes the decision. So you can make it two ways, but the way I find it most appealing, like you build a machine to make the decision on its own, and you want to bake into the machine a decision-making process, and that's where how we use causal inference in the industry is like the causal inference part is the counterfactual brain of the machine. Like the machine needs to understand what will happen if it gives all the decisions that it can give. And based on what will happen out of all the decisions it can make, it then picks the decision which think it's optimal. And think it's optimal is essentially an estimation given by your causal inference model. I don't know if it answers. I feel that the answer was a little bit vague. So if you want me to specify something, please feel free to add some follow-up comment. I understand that most of the projects you work at Nubank are behind scrutiny, privacy policies, but can you give, at least in general terms, a concrete examples? Oh, I just gave this. So again, cannot go into the details, but some of the big decisions that a bank needs to make is interest rates and how much money it gives to people, and you can use causal inference to make those decisions. Another thing, but that's not related to banking, I think it's more general, is related to marketing. So essentially, who and how much you spend, who do you send advertisement to, and how much you spend on advertisement is also a decision that multiple companies has to make. And this is a causal inference approach. Like, you have to understand how to allocate your marketing budget and which people you target for your marketing campaigns. Just another side comment on the banking. I don't know how many of you are from economics, but there is a very well-known part from microeconometrics, which is called price discrimination. So although the name sounds bad, essentially means charging different prices to different customers. So usually companies cannot do that. They're forced to charge the same price for everyone. There are some exceptions. For instance, air travel companies. Yes, they are restricted. They can charge the same price for everyone, but they can change the price given every day. So what they do is something called intertemporal price discrimination, where instead of trying to figure out what price to charge every customer, they try to figure out what price to charge every day. So it's almost the same problem, but the unit of analysis changes from customer to prices. Banking is a very interesting industry for causal inference, because the price in bank is the interest rates, and it's not only allowed for a bank to charge different interest rates to different customers, it's actually desired. Like, you don't expect a bank to charge the same interest rate for a very risky customer and a very low risk customer. Like, this is the standard of the industries to charge different interest rates, which is why I think banking is a very fun place to be if you want to work with causal inference.
I love those examples. Treating they as the unit and treating people as the unit. I have a question. So I think I understand most of the book, but there's the one concept that just, like, I have no idea what this is about. It's synthetic control. I was wondering if we could talk a little bit about what is this about? Like, when do we use it? It's just like a really hard concept for me.
Okay. So live question on how to explain a very complex topic in very short amount of time. I'll do my best.
So sorry. I know it's so complex.
Do you understood, like, the concept of difference in difference?
Yes. I think so. It's for
Great.
panel data. Difference is if you have a little more data, but for synthetic control, it's when you only have maybe one treatment unit. That's yeah, I guess that's so far what I am understanding, but the rest, I'm not sure.
You're halfway there. So what you do in difference is you try to leverage correlations between units, so between people. So if you treat, let's say you take a bunch of people and you don't treat them, and you see how they behave over time. And then you take another group of people, you treat them in one period, and then you see how they behave after the treatment. This is very interesting because you can compare the treatment group with itself before the treatment and the treatment group with the control group, which was not treated. So it essentially leveraging two sorts of correlation: the correlation between people in the treatment and in the control, and the treatment with the treatment itself prior to the treatment. How do we go from that to synthetic control? So synthetic control is, let's say you don't have a bunch of people, you only have like a few ones. So in the case where you cannot randomize people in marketing, but you can randomize a certain geographic location, you have one unit or very few units that units of analysis. So doing unit-wise comparison feels a little bit cumbersome. So what you do is essentially you flip the data from unit. So what you usually have in difference in difference is that, well, you have each unit and you have multiple time periods. In synthetic control, you flip that around, so the time periods become the unit, and the unit becomes the time periods. So essentially, you flip all that around. And what you do then is that you'll find correlation with the entire time series of each unit with the treatment group that you have. So what you do is that you have the treatment group. You have the treatment group, and it has a time series of how it behaves prior to the treatment. And what you do is you try to reconstruct the time series of the treatment group using the other time series of the other units of analysis. So one way to do that, which is the synthetic control, is that you're going to find a sort of a weighted average where you take all the other time series of all the other units that you have and try to reconstruct the time series of the treatment group. So essentially, you created this is what is called a synthetic control. You create a combination of units which reconstruct the behavior of the treatment units prior to the treatment. This is one way, but there's a bunch of other ways. Like you don't need exactly an average. This is the canonical way, but you can go crazy. You can use whatever sort of time series model you want to, essentially to predict the behavior of the treatment group prior to the treatment. So you have a very good prediction of how the treatment groups behaves. Have a very good prediction of how the treatment groups behave. And then you make predictions for that after the treatment. So if your model is good, the treatment group should behave as your model is predicting. And the only reason it does not is because you applied a shock to it. So the treatment. You essentially apply the treatment, which makes the outcome go either up or down, whatever the treatment effect is. And because of that, the model that you build is going to make mistakes. And the mistakes, you're going to say that all the mistakes that the model is making is due to the treatment, the shock that you apply. So essentially, the difference between what you're predicting and what you observed, you call that a treatment effect. So this is the essential thing that you need to understand of synthetic control. Like you're doing a time series forecasting problem, like you're forecasting the behavior of the treatment groups, and you're projecting that forecast after the treatment itself and computing the difference between what happened and what you predict would happen.
That makes so much sense. Thank you so much. So it's like a time series prediction problem, essentially.
It's exactly a time series prediction problem.
Awesome. I have one final question. So I think I may have the answer. So when do you use ATE versus ATT? Is it because some designs you can't get ATE, like for panel data, difference in difference, synthetic control, you can only get the average effect for the treated. That's why there is a difference. Is that because, does that mean like normal times we would use ATE, and for like those designs we use ATT?
I confess I have to study more about this. I know that Scott did a bunch of series on why ATT is interesting in the industry. My default answer would be like, this is more of a limitation than a desire. Like if we could, we would use the AT, but sometimes we can't. So for instance, in panel data, what you're usually interested in is what is the effect of deploying this marketing campaign. This is what you get. But this is what you're interested. You're interested in understanding what's the effect, the average effect of this campaign. But what you get if you run a panel data analysis is what was the effect on the states, let's say, where it did deploy the campaign. And they're not equal. Like sometimes you deploy the marketing campaign in states that are different from the other ones from the average state, let's say. So they're not equal to each other, but you only get the ATT because that's a limitation. On other situations, you actually want the ATT. I think I mentioned this in chapter 12. Chapter 12, which is if you're doing some sort of IV. So let's say you have a prime. I think that was the example I gave. You have a price segment of your customer. So these are very special customer. I want to treat them very specially, and I want to see how treating them specially is influencing my business. So I'm essentially evaluating my prime segment customer. In this case, you don't care about the average effect of treating everyone very nicely, because you're only going to treat those very special customers. So in this case, you're only interested in the ATT. You don't really care about what will happen if you took the treatment and generalize it to everyone else. So I think it's very context specific. I need to read Scott's series about this. He talks a lot more about this. But there is this, I think, this distinction. You look at ATT because it's a limitation. Even though you want the ATE, you can only get the ATT. But sometimes you only care about a very specific group of people, so you treat them and see, and you can evaluate the ATT on them because they were the ones you treated. Okay. I was looking at the chat. I'm curious for your intake when causal inference is where causal inference is heading in the near future in the industry, and what subfield of it may need further future advancements. The second one is easy to answer. I think we need advancements in metrics for causal inference. It's very hard to build trustworthy metrics for causal inference, and if we could find it, it will essentially make everything much easier. Like we would be able to treat causal inference as a machine learning problem, and that would simplify things a lot. The other place where I think we could do some, and where I think the industry is heading, is causal reinforcement learning, because the problems are very much aligned. Like if you look into reinforcement learning from the perspective of computer science, it's the same problem as a causal inference problem. Like you have actions and you want to build a decision-making rule which allocates the actions in a way to maximize the reward. It's the same problem of causal inference over time. Like we're applying causal inference sequentially and seeing what happens. So I think this is where the industry is going to go. It's how can we leverage stuff from causal inference into and bake it into our reinforcement learning settings. Like apply debiasing would probably already help a bunch. And how can we leverage causal inference to design better ways to sample data, to gather data more efficiently? I think that's probably where the industry is going in the near future. Question. Okay. Was there a particular motivation behind writing causal inference in Python? While reading it for translation, I noticed a strong emphasis on addressing. Yeah, that was the on addressing industry-related matters. I think that's the motivation. Like I read a bunch of causal inference book. I could not find one that was targeted at industry and applications. So because I've been working with that for a bunch of time, I felt that I had the expertise to write such a book, and that led me to causal inference in Python. I had translated your work, Causal Inference. Oh, so you were the one who translated. Thanks a lot. I think that's very appreciated. And now you're translate. I'm very glad to see that the book is gaining like translation in Korean. I wished I could read it. I cannot. But I hope so. I will not be able to see if you did a good job, but I really trust you, and that's the only thing I can do.
Awesome. I guess thank you so much for the amazing discussion. I feel like I have learned so much, and we're really grateful and honored to have you here today. Yeah, for people who are watching, please go get a copy of this amazing book. I highly recommend it, especially if you're a data scientist or a data analyst. Yeah, thank you everyone for watching, and happy reading. Bye-bye.
Thanks again for the invite, Sophia. Have a great day, everyone. Bye bye.
Bye.